our next speaker, Dr. Tapan Kumar Hota. I saw Dr. Hota is here. So can you?
Yeah, good afternoon, Sagasi. I'm here.
Good afternoon, sir. So let me just quickly introduce Dr. Hota with a formal manner. So Dr. Tapan Kumar Hota is an assistant professor in SRM University, Andhra Pradesh. He obtained his doctoral degree, PhD degree from the Indian Institute of Technology, Ropar, and his master's degree was obtained from Indian Institute of Science, Bangalore. Also, he held a position as an Indo-US postdoctoral fellow in Texas A&M University. And his primary focus of research lies in the examination of transient growth and mathematical analysis pertaining to an interfacial instability commonly referred to as an viscous fingering. So over to you, sir. Please try to share your screen.
Yeah. Just a minute, I'll wait.
Sure, no problem.
Is the screen visible?
Yes, sir, it's visible. If you make it full screen, yes, perfect. Perfect. Okay, thank you. Please go ahead.
Okay, so
we are recording, so it's fine with you, right?
yes.
Yes.
Yeah, absolutely.
You responded to me giving consent, but I just wanted to confirm once. Yeah, thank you.
Yes. Okay, thank you. So good afternoon, all of you, online, offline, and India, abroad, everybody, and big thank you to the organizer, Satyajit, and colleagues. So what I'm going to talk about is that a very naive approach to understand the dynamic mode decomposition and a particular application to a certain thing called the interfacial stability, a particular stability that viscous fingering. So here is my content. So let me give you a disclaimer. Whatever I'm going to describe is almost all known in the various scientific community. I put it together so that I can give a broad perspective of it. So now first what we do is that I will describe something called the layman point of view of what is the hydrodynamic stability, and a layman point of view again how the spectrum of the governing equations describe the stability of a dynamical system, hence describe the hydrodynamic stability. A particular interfacial instability, then I will describe something called the viscous fingering. And the main theme of this today's gathering is about the something very crucial and very important one. Although we have all of us miss Nathan's talk, if he could make it, he could make it. We'll be very happy with all of us, and we will be very happy. So we'll see its variant and the naive dynamic mode decomposition, and some of the things what I wish to do, I will put it in the conclusion. So let us look at what is hydrodynamic stability. So as Chirodeep described very brilliantly, I cannot say it that nice way. So thanks to Chirodeep, you are saying that you don't know a little bit of maths, but you are very good at it, and you describe it very nicely. So comes to the thing. So any flow, any system, physical system, susceptible to any kind of small to moderate type of disturbances. So hence, in particular in the fluid flow, one has to look at if somebody provided some kind of small disturbance or the moderate amplitude disturbance, how the system behaves. If it is returned back to eventually return back to its base state or equilibrium state, then we say it's stable. If it is going into the different phases, that is the transition to different phases, or did not return back to its equilibrium position, that is we call the unstable situation. Okay. So to this schematic to show that you have a base state or equilibrium state, you provide some kind of perturbation U cap, and total flow is about the UB and the U cap. Now what you see is that stable, unstable situation. This is from the Cohen-Kundu book and the Drazen's book. So all the copyright goes to these books wherever possible, wherever I got it. So I have cited it. If I miss something, please let me know. I could modify and send it, the slides even. So this position, where the red dot, you assume that it is a ball. If you apply a small force to it, it will be roll left, right, and return back to its original position. So it is, we call it the stable situation or stable position of that ball. And for the second figure, which is unstable, which is the peak of top of the say mountain. So a small force or something disturbance, it will be rolled down to different state. So it is unstable. A neutral stable, you have a flat surface. The amount of force you applied, it will be rolled down to that much of distance. It's so fate of it is dynamics of it. It's eventually the same at the t equal to 0 to t equal to delta t. And the conditional stability, it is about the like a small force, it will be rolled down and come back to its original position. A moderate, maybe a little bit higher amplitude, it may be go to the another state. So it is conditional stable. So this is the layman's point of view of what is called the stability analysis. Now, how one would perceive in fluid flow analysis or any kind of mathematical approach. So suppose you have the governing equation dou q by dou t equal to n q. N is some linear operator operating on certain uh, space, and q is just dead variables. So what you do, you want to study this the dynamics or the stability of the system that is governed by this partial differential equation. So what people, there are two ways to understand it. You do the full nonlinear simulation using the whatever computational facility you have, or what you can do is the less expensive and quite familiarized to the most of the scientific communities, the linear stability analysis. What it does, it has two steps to be formally. You have a base state to be derived from your system. Okay. Then around the base state, you just take a small amplitude Taylor series expansion. So, or a perturbation thing, regular perturbation thing. So you epsilon square term, you just remove it, assuming that epsilon is a very, very small quantity, called the positive. Then you substitute this expression into original dou q by dou t equal to n q. So what you get eventually is that a linearized version of the nonlinear equation. Still, we have the PDE. So the next step of the linearization is the linear stability analysis, or the original equation is the diagonalization or separation of variable to the precise to say. So what you do, you separate the time and space variables, and we call this e to the power lambda t. Lambda is your some complex number. We call it its growth rate. So if the real part of lambda is positive, it will grow. If the real part of lambda is negative, it will damped out. If real part of lambda equal to 0, it is oscillatory one, and there's a neutral stability. So once you substitute this q tilde, the expression as small q e to the power lambda t, out of this linearized equation, you will get a eigenvalue problem. Now, once you study this eigenvalue problem, find out the lambda q respectively, and state whether the system is stable or unstable depending on the real part of the lambda. So a little bit of discussion why this linear stability, although there are a lot of numerical resources are available, computational things are quite evolved. So what you do is that why we study for the linear stability analysis. As I said, it is much cheaper than the what you do in the nonlinear system. Okay. Second thing is that it may happen that the early time evolution of the certain base flow or the fluid flow, we can easily capturable through this very cheaper way. So computationally, it will be feasible. So we can predict certain critical parameter associated with the fluid flow. Now let's come back to a little bit of linear algebra. To understand, to going for the further understanding the dynamic mode decomposition, or so the higher version of this, exactly the eigenmode decomposition. So now suppose you have a n cross n a matrix having complex coefficients. Now a vector v is called a eigenvector, non-zero vector is called eigenvector if it is satisfied this equation 1. Lambda is called the eigenvalue. It can be complex. But let us look at this schematic. Now, what this schematic is saying that suppose you have the 2 by 2 system, one lambda, the one eigenvalue of the system is 1.2, another is 0.5, precisely to say that lambda 1, lambda 2 are real number, and that one is greater than 1 and the other is the 0.5. So what you do, if you keep on iterating, okay, iteration, AK you can keep it. So along this direction of the lambda 1, which is the magnitude greater than 1, everything will stretched, and in other way lambda 2 less than mod less than 1, it is contracting. So that is what the iteratively when you apply the eigenvectors vector associated with the eigenvalues, what it does. Now that is about the eigenvalue. So why this in the diagonalization procedure or the second step of the linearization, why it works for the various flow. Okay, two of the good examples Chirodeep told. Okay, plain quiet flow and thing. So let us look at why the eigenmode decomposition works for this kind of fluid flow analysis. Suppose you have the matrix A, which n by n matrix, complex entries, maybe complex entries. So if A has n linearly independent eigenvectors, indexed as b1, b2 to bn, and corresponding eigenvalues are lambda 1 to lambda n. So we can write down as the system as the A V equal to lambda V or V lambda. Okay. So precisely to say A can be written as V lambda capital lambda V inverse. This is what we call the equation 2 in this lime color. That is what we call the eigenmode decomposition. And in mathematical term, what in linear algebra, what we call is that the if a matrix is diagonalizable, if it is satisfied this equation number 2, we call that diagonalizable or non-defective. Okay. And one of the key theorem for the linear algebra is that every normal matrix, that means which matrix commute with its Hermitian part or the adjoint part, is always diagonalized. So whenever for any fluid system, the linear stability analysis gives the correct prediction for the critical flow parameter, without any doubt, one can vouch that the underlying matrix, whatever we are getting after the linearization, must be a normal matrix or very close to a normal matrix. And if a matrix doesn't satisfy the equation 2, it can satisfy other decomposition thing similar to the eigen decomposition. That is what we call the canonical Jordan form, and we term it as defective. Now, how these eigenvalues, eigenvectors, and the hydrodynamic stability and how they are related? It is related through this study of the dynamical system. Suppose we have the dynamical system equation number 3, V dot equal to AVT. So alpha here is a system parameter. Okay, so in the first lecture, what you see that the system parameter can be the Reynolds number. So V dot means is the time derivative of the V. And if A doesn't depend on T, independent of T, we call it the autonomous. If A depends on T, that is called the non-autonomous or the time varying system. Now, how it is related? If A is an autonomous system, normal, that is non-defective. That means we can have the what do you call that? Eigenmode decomposition can be possible. Then this dynamical system equation number 3, V dot equal to AV, has the solution of this form V exponential of T lambda V inverse V naught. V naught is the initial state. Okay. So from here, you can find out its energy or the stability analysis or something or the other, whatever you like to do, you can do. And what will be the critical alpha for which these things can be increasing to find out the norm. If the norm is positive for that particular alpha, then the system goes to unstable. Often what happened is that instead of the general, normal eigenvalue, some mass matrix been multiplied to the left hand side of the equation 3, then in that case we get a generalized eigenvalue problem. But the theme of the understanding of how the stability can be done for the linear dynamical system, same as for the without any B matrix or B to be an identity matrix. So how the stability be established? First thing is that eigenvalues determine from this, if A is a normal matrix, the solution is the V exponential T lambda V inverse. This lambda describe the long-term behavior of the dynamical system. For example, this one, the x-axis is about the real part of the lambda and the y-axis is your imaginary part of the lambda. Okay. So if you go by the green dots, that means what? The imaginary part is, like you have the only the real values are there. Okay. So if it is the negative real part of e to the power minus of something t, it will be goes on decreasing. Okay. And if it is a lambda, real lambda is 0 and the imaginary part of lambda is 0, it is e to the power t times 0, that is constant. And if it is the lambda value is positive, it will be goes on increasing, that is the amplification. Now, if the imaginary part is there, then what is going to happen is that the oscillatory system will be observed along with how the amplitude of the waves will be depending on the real part of lambda. Real part of lambda is negative means it will be damped out. If it is real part of lambda is high, it will be keep on amplitude will be keep on increasing. So in essence, in the fluid dynamics community, this eigenmode decomposition or the spectral theorem for the normal operator or the normal matrices is known as the modal decomposition. Okay. So what the special feature of it is that it can describe the what is the like most dominated eigenvalues, eigenvectors, so that growth rate and the frequency can be determined in terms of the energy. And further is that this modal decomposition, when the A is not a normal matrix, it cannot be directly cannot be applicable. It is only applicable if it is the matrix is a normal or near to normal. If it is not, then we have to see from some other alternatives. So one of the alternative is about that the model reduction methods or the data driven methods. Again, it is based on the eigenvalues and eigenvectors, but it is not exactly the way the model analysis or the diagonalization been imposed throughout the so many years. So we will look at that one. So what my understanding about the so-called the understanding of this naive way of understanding dynamical decomposition is that dynamic mode decomposition is that it is just an extension of the normal mode or the modal decomposition or the spectral decomposition to a higher level with some kind of flexibility. We will see what kind of flexibility we'll get it. So that method particularly popularized by two group or the two people. So one way our first speaker we missed Nathan and Steve, and another person is the Peter Schmid in the celebrated paper of 2010. So what he supplies is that how to understand the snapshot method based method, and the heart of the matter is that always the eigenmodes and eigenvectors, but in a different flavor. So what it is that you have the data, either data from the numerical simulations, nonlinear simulations, or from the experimental data. So say for a for abstract notion, suppose you have this dynamical system, dx equals to dx by dt equal to fx t alpha, and this f represents your dynamics, x is a Rn vector. Okay, so state of our dynamical system, alpha is the system parameter. So let us assume that our fluid flow is either it is in 2 dimension or 3 dimension or so. The x vector for the each time it will be a column vector. Okay, for each time tk. So first thing you do, stack it over for each time one over the other, or for the each coordinate vector you stack it for the each time. Okay. So what I do here is that instead of writing this column vectors, one column vector ends, then the second column vector beneath it, then the third, then the fourth and something. So I give rise to this part. Okay. So we have this system. So X our flow variable, R denotes the spatial coordinate and K denotes the kth time. Now, two ways you can arrange it. One, you have for each time you have the snapshots, you keep on stacking from left to right, or for each X variable or the T for the X variable, you can stack it from the bottom to top. Okay. One way you can get the temporal analysis, and another one you'll get the spatial stability analysis. So once you stack it, what you'll do? So you have, suppose, the data x1, t1, x at t2, x2, tm plus 1, say. Okay. So what you do is that assume the first m vector into first, and the second one just shift to the next. Instead of the time t1, you start with the time t2. Then naive decomposition, dynamic decomposition is what we are looking at. Suppose you have the data with you, experimental or numerical data. What it does, your system, what it does. Xt1 vector, when you apply on it, it will go to the xt2. When you apply to the xt2, it will go to the xt3. In essence, we require a operator A, which can send the x1m matrix to the x2m plus 1 matrix. Okay. So how do you do? Because this is a, not a square matrix, so general inverse cannot be possible. So what you do, you find out the generalized inverse or the pseudo inverse, which in mathematical term we call it as the Moore-Penrose inverse, not the square matrix inverse, but it is a rectangular one. Just find out the Moore-Penrose inverse, multiply to the right side of the x2m1 to find out A. That's it. Very simple, mathematically abstract way. That is very nice. Now you find out the eigenmodes of this so-called operator. You know the x2m plus 1, you know x1m, you find out the pseudo inverse of it, of the x1m, and hence find out the eigenvector. Okay. And each the mode corresponding to a particular eigenvalue. So whatever the modes you get it, we let us don't dwell on that right now, that the dynamic mode or something, we call it the modes right now. Okay. So this is what the dynamic mode decomposition in a very, very simple language. Now the question is that how to find out that A? Is it so easy to find out the Moore-Penrose inverse? That is what the challenges is. First thing, before going to find out the Moore-Penrose inverse or the finding out the A, what you need is that the number of snapshots you are taking for the temporal analysis is that the number of component, whatever you are taking, it should be small. That means in terms of that, the m should be very, very less than n. Now, to find out the A explicitly, or to find out the Moore-Penrose inverse and the multiply to the x2m plus 1, it can be done by this minimization problem, where f denote the Frobenius norm. Frobenius norm, why? Because it is a simple extension of the Rn vector, the standard Euclidean norm or the distance vector to the matrix norm. That's why that is a more natural norm to be precisely taken. So let us look at how we can do that in practice. So we have this equation, the dynamical system for us. N is the number of spatial points saved per time snapshots, and M is the number of snapshots taken. Now DMD, or the dynamic mode decomposition, considered approximately locally linear dynamical system. So this A, whatever we are getting over here, it is going to be a linear matrix if you have a discrete data. If you have a continuous data, it is going to be a linear operator. Okay, but remember, your equation may be a nonlinear dynamical system. So For the continuous case, you have this equation 7, and the solution of it can be decomposed as, or again the same, the separation of variable bj phi j e to the power e omega j t, or in a compact form capital phi e capital omega t b vector. What is this phi j's? Phi j's are the eigenvector of this continuous operator A, which we call the dynamic modes, or the okay, yeah, the eigenmodes are called the dynamic modes, and the omega j are called the corresponding eigenvalues of A, determine the growth rate, and bj are the coefficient related to the initial state. It can be determined as the Moore-Penrose inverse times the initial state of it. That is about the continuous case. For the discrete case, what you do, you have the system at the time k plus 1, it has to determine by A times the time, the data or the observables at the time k. So you what is capital A? Capital A is the e to the power, that scripted A, and the dt. Dt is your at what time steps for the time between two different snapshots, what it is, that is the dt, small dt. So here also the solution will be turns out to be the, assuming it to be again a separation of variable bj phi j lambda j k. So in compact form phi lambda k b vector. The phi j omega j again the same as the case of the continuous case. These bj's are the again the related to the initial point state. Here the initial state will be x1 instead of the x vector 0 in the continuous case this. So what it does, the DMD. DMD is that here these phi j's, unlike the spectral decomposition, which assume to be the vectors to be orthogonal. Okay, here assumes simply to be the linearly independent, nothing else. Okay, so these phi j's are going to be the simply linearly independent things, but no guarantee that it is going to be the orthogonal. Second thing is that once you find out that this decomposition, both the decomposition, eigenmode decomposition and the naive dynamic mode decomposition, what is the common feature over here is that they use the same separation of variable. Okay, so the space variable and the time variable, they are separating out. So main goal of the DMD is to find out this system matrix or the subsequently the discrete time domain A. Now, what is the main goal? Main goal is to this minimizing this thing. So what is the big deal? Big deal is that we don't have to do all the datas. We can produce a model reduction way. So a low rank eigenmode decomposition is only required to find out this minimum or the finding out this minimum of this thing. Okay, we need to find this in what sense we have to solve this minimization problem in the least square sense, or in a statistical language we have to find out a little bit of linear or quadratic regression analysis. So the best fit to this situation approximate the solution to the system of linear equations stated and minimizes this Frobenius now, and which will be obtained by this Moore-Penrose pseudo inverse. Now let us look at how it can be done. So the more detail about this analysis and something, please go to the Peter's Schmid work of 2010 JFM work, and Steven Bunter's Tyra et al.'s very good this review article, model analysis of fluid flow. They have a lot of things to talk about, particularly POD, SBD, and so many things. So let us concentrate on our naive dynamic mode decomposition. I will tell why I am calling it the naive one. So you have these snapshots. Okay. So first M you assume to be x1 M, and x2 M1 will be shifted from the second to the last one. Now what you do the singular value decomposition of the first x1 M. You will get U sigma V star. Just keep an eye on this guy U. That is what the main goal. So what is A? A is your x2 m1 x1 m dagger. That is the Moore-Penrose inverse. So Moore-Penrose inverse is exactly the whatever you are getting the this singular value decomposition. Now, as I said, keep an eye on this U, that you determine the PODs. First, you stack it to the first M, then the separate it to the second to the M plus 1, all the snapshots, you get x1 M to x2 M plus 1, do the singular value decomposition to the x1 M data. Then you find out A from the using the main Moore-Penrose inverse of the x1 M. Now look at for the U. So what you do, you take a projection onto the space of the space where the U lies on. So R cross R. If the rank of U is R, just the projection onto it. So you'll get U star AU. That is the A tilde. Now you substitute what you get the A, you will get the expression for A tilde. Now this guy A tilde is our theme, not the A whatever we require from the this Moore-Penrose step 4. So find out the eigenmode decomposition of this projected matrix onto this principal orthogonal modes wherever they're living. A tilde W equal to lambda omega. Now reconstruct the eigenmode decomposition of the original A from the eigenmode decomposition of this low rank matrix A tilde. In particular, the eigenvalues of A are the simply the lambda determined from A tilde, and the eigenvectors of capital A, those we call it the dynamic modes are given by the columns phi, that is x to m plus 1 p sigma inverse w. So once you get phi, you can get bj, you get the lambdas, then multiply together to get your the solutions of the each of these things. So you can reconstruct the data, whatever you have from the numerics or from the experiment. I hope it is not going to be one-sided and not too much involved in linear algebra part. So if you have any question or something, just let me know. Can I carry?
Yes, I think you can carry. If someone has any question, can please put in the chat box so that we can address it after the finishing of this lecture.
Stop.
You can carry, sir, no problem.
Yeah. So this is the famous thing, famous, like the so-called the poster for this DMD. Now, what we have done, the pictorial, let us understand. You have these snapshots x1, x2, x3 to xm. So x contains the x1, x2, xm minus 1, and x dash contains the x2 to xm. So you want to find out the best fit A, which can send this x to x dash by finding out the Moore-Penrose inverse of x dagger. So use the little bit of regression to find out what is A by the first followed by the SBD, then the low rank PO projection to the SBD of the PODs, and then whatever the low rank matrix A tilde you get out of A, those eigenvalues and eigenvector, it gives you the dynamic modes. So this is the way you can get it. So you can get also can make some kind of future prediction. If you know the TK, what is the state, you know A already, which governing, which sending the this data to X tilde, you can get for a future prediction. But how much you can do that, it depends upon the your system and how good this A been. Remember, your system is non-linear. Your experimental data comes from a very different environment. You are approximating all this data to X dash by a linear matrix or a linear operator. So now let us talk about the viscous fingering part. So what is viscous fingering? Just look at the first panel of this. Blue fluid is a less viscous and red one is a high viscous fluid. When a less viscous fluid pushes or try to displace the high viscous fluid, the interface deforms and finger-like projection comes. That is why it is called a viscous fingering problem. Okay. So it is an interfacial problem. instability, interface deforms, so interfacial instability, viscous fingering because finger-like projection comes, viscous because the viscosity contrast. So let us understand how people did. In particular, Satyajit knows more than me to how to do the nonlinear simulation. So whatever the experiment, the numerical simulation data I'm going to use and apply the DMD. This is the way I'm going to do using the console. So we have taken the rectilinear domain, computational domain of x direction 2 meter, y direction 0.5 meter in console. So these are the governing equations. First one is the continuity equation, incompressibility condition. Second one is about the Darcy law, flow in porous media. Third one is about the convection diffusion equation, how the species transported. So for the Darcy law, DL module and the transportation of diluted species in the porous media, TDS model for this one, the 13 equation. So we have used something called the Delanoid tessellation of the triangular mesh, and running time is 500 seconds and DT taken to be the 0.5. And log mobility ratio, that means the viscosity contrast mu1, mu2 and mobility contrast between the two fluids is taken to be the R equal to 2. So more detail about this console implementation and the governing equation, you can look at the Holmes's and from Satyajit's paper. So here we go. The first panel is the reconstruction of data from the DMD, and the second B1 is from the simulation. Okay, and the timestamp from the bottom to top to bottom is 50, 100, 200, and 450. To a naked eye, it looks good, and somehow we can able to reconstruct the data. So to visualize how much error we have committed, we have plotted something for each time the data reconstructed from the DMD and the numerical simulation we have computed. Is error is maximum error is going to be the 1.2%, the absolute relative error. Okay, 1.2%, which is good enough. Now let us look at another one. I'll go to this is the reconstruction of data. I will look at the coherent structure or the dynamic mode structures also. Let's look at this radial fingering. This is about experimental data. And thanks Professor Manoranjan from IIT Roper. He gave an opportunity to my student to visit there, and he conducted the experiment. It is a part of the experiment, not the full. And it has been done by other groups also. So what we have is that again, the less viscous fluid, the blue one is displacing a white one, the high viscous one. And there are two circular plates having the gap 0.5 mm, and the log mobility ratio between the white fluid and the blue fluid is taken to be 3. Now, this is the data constructed from the first panel is constructed from the dynamic mode decomposition. Second one is from the experiment. In this case, what we are getting is that in comparison to the numerical part, the rectilinear thing, in the radial one, we are getting a very good comparison over here. And for this experimental, the figure has 1870 by 858 pixels each. So the SAMs are 1 second, 10, 20, and 30 seconds. But when we plotted the absolute relative error, you can see that there is a very zigzag things in comparison to the rectilinear part, which is a very smooth one. Initially, it is increasing but decreasing, right? But here it is goes up and down, up and down, up and down. And the maximum error we committed by the reconstruction of the data from the DMD is that about the 2%. No. Why it is this the zigzag thing? Of course, when you do the experiment, this part, there are a lot of noises are there. And after a lot of iterations of using, adaptive median, swivel things and something, we could able to reduce some of the noises, but not clearly. That is why there is a zigzagness in some point around after 25, the error shoot up a little bit. But eventually it is bound by the 2%. Now, what is the strength of this using this DMD? we could able to have the numerical data or the experimental data, we can reconstruct the data. Okay, further analysis will be required for the various structure to understand, so that different type of parameters, different type of scalings, or the something how the different parameter really help, or what does to the stability or instability part. Let us overview about this strength of this naive DMD. First thing, it doesn't require pre-assumption or knowledge of the dynamics. Okay. Entirely, it is data driven. Under certain conditions, this DMD, whatever we have done, or for these two problems, what we have done for the radial and the rectilinear one, it is can be approximated to the Koopman operator. Koopman operator, what the DMD we have done, it is a discrete one. Okay. For the continuous one, it can be approximated to the Koopman operator, which can deal with the nonlinear data. Okay, appropriately. Again, it is lives in the infinite dimensional vector space, but it is linear operator. DMD modes can isolate specific dynamical structures, particularly frequency part, and we will see in a minute, it can be customizable. What are the difficulties or the weakness? It is all about nothing, if it is the, is a very good full-proof approach of it, it is very good. There should be a full stop, no more discussion, and everybody could, blindfoldedly use it. But there are some precautions, and there are some kind of cons are there. So first thing is that it can be difficult to determine which modes are the more physically relevant from the DMD mode decompositions. Often what happened is that this is a quite unreliable for the non-linear system, because whatever you are approximating, it is a linear operator A or A tilde. And the output of DMD can be sensitive to noisy data. And DMD is generally meant for the autonomous system. Initially, the naive DMD, whatever I have described or been proposed in most of the literatures, and DMD modes are not orthogonal. And this DMD modes fundamentally depends on the separation of variable, like the eigenmode decomposition or the modal analysis. So it cannot be readily extended to traveling wave motions. And DMD modes finally typically doesn't work for the systems of highly intermediate dynamics. Like there are different type of transitions, so different type of scales are available in your fluid flow system. Then it will be typically this naive DMD is not going to work. So here are the modes that we calculated from our radial flow. If you look at the mode 2, which assumed to be the, from our analysis, the most we call that dominant mode, this one. Apart from that, when you calculate the singular value decomposition, the singular values or the PODs, energy of the PODs, if you calculated it, after around 70, we have the almost data we have taken. The total experimental data is around 1,200 or something. Only 150 snapshots been taken to consider this one to analyze. After 70 or 80, all the data, the energy is so low that it doesn't require any kind of attention. So 70 to 80 modes will be good enough. But what you see is that after the mode 50s onwards, the imaginary component of the DMD modes, they are vanishing. Okay, that means what the imaginary plots represent, it represents the phase shifts of mode. Particularly if you look at the attention to the mode 70, it is a static feature. That means it is not dynamic. Hence, this method does not show whether the modes occur in any particular subset of the data set or throughout the data set. Okay, so that's why I took, by physical inspection to find out which mode you really require for your analysis, segregating the things, it will be a little bit difficult thing. One more minute. How much seconds I have?
Sir, it's almost the time. So if you can finish it.
Yeah, just that's what I'm saying. Okay. So one way to understand for this my problem of the viscous fingering is that the proposal is that the multi-resolution, where the multi-scales are available. Okay, so what you do in the multi-resolution or MRDMD is that you divide the whole data into two sets, the pink and gray. Okay, and at each level you throw out, for example, the second panel, middle panel, if you look at it. Okay, so middle panel is the showing the DMD spectrum. Index 1, the what you call the 5K1, the blue dots, slow dynamics modes. The blue second one, peak 5K2, these are the modes of the second level and the third level. Whatever be the slow modes, you the segregating at the each of this level, throw it out. Whatever the first modes are required, that is only the your required modes, which are you are going to concentrate on. So whatever I have presented or the underlying the data driven snapshots and something, all things, this is the book that look at it. I did not manufacture any theory or any theorem or any basics from my own. This is the book to look at. Final few words. This particular viscous fingering things, it is a transient phenomena. That means what the underlying system is the non-autonomous system. It is required that this physical laws due to the temporal, this temporal variations should be, addressed properly, or it needs to be accommodated in DMD. DMD has a lot of potential, but data-driven learning approach using the DMD for this non-autonomous system is really a big deal. Few approaches successfully done, but only for the periodic or quasi-periodic systems. So this is the paper by Zhang in 2019 in SRM. And last acknowledgement, Professor Manoranjan Misra from this giving the permission to use the FTRL lab for the experiment, SCRB for this financial support, and my university, SRM University, for the computer facility. Thank you, the organizer.
Thank you very much, Professor Hota. I would like to ask the participants if you have any question. You please, for the online participant, please feel free to unmute yourself and you can ask. Or is there any question from the offline participants? They can ask question to our speaker.
Can I ask one question quickly?
Yeah.
Okay, so you have already partly answered my question. So theory that you were explaining towards the beginning, it's all for autonomous system, right?
Right.
Now, given that for certain non-autonomous system like quasi-periodic or periodic cases, do the same theory works, or for quasi-periodic or periodic also the theory changes slightly from the autonomous non-autonomous?
Yeah, it is slightly changing, nothing big deal. It's very slightly, but I did not know the exactly how to implement that. One way is that what the Nathan and Stevens book, if you look at on the paper recently 2016, what they have written is that one is the multi-resolution DMD, another is the physics-driven DMD. Those are the two, next level thing. And for the non-autonomous quasi-periodic and periodic thing, what they are looking at is that instead of looking at the the eigenvalues, certain trajectories and the manifolds they are talking, I don't understand right. Right now I don't have did not get into that. I did not understand that part.
Okay. And coming to one of your viscous fingering results, like the first one you showed reconstructed results and you compared with the experimental things. So you are showing half of the domain, or is it
this
because
one
of radial symmetry?
Yeah, this one is the half of the domain. Yeah, half of the domain. The full domain should be looks like this like this schematic, but there is a pipe and something. So to while we are doing the image processing, there is some issues.
Yeah, I understand. Because of that image is coming with the injection port and everything, which is making it noisy data. So you just wanted to truncate that portion and reproduce the part which is clear.
Right.
Okay. Okay. Yeah. Thank you.
I think there is a question in the chat box. The question is there any scenario where DMD fails to reconstruct original flow field with good accuracy?
Of course. Of course. So I'm telling, look at this book. There are first chapter, second or third chapter. He gives very simple example where DMD fails.
Is there any other question from the audience section?
I will ask one more. So whatever amount of computation you had to do for training or processing, what's the computational cost, or what kind of computational facilities you need to use?
First thing is that let me tell you, since it is based on the model reduction, so you require less number of sample to train. For my console thing, I'm telling you, whole data for one simulation 500 seconds. That's what I have done. It is around 2.5 GB data. Altogether, different features are there. If I collecting all these snapshots, that is around say 300 MB or 340 MB. While I am using this one, I'm choosing only around 196 snapshots, which is maybe 25 to 30 MB.
Okay.
Second thing, what is that your question, Satyajit?
Yeah, that's one. And the second thing is that how much time it takes to complete all the training and other things on.
Hardly, for my case, hardly take maybe 3 to 10 seconds, depending on how many projection level you are to keep on changing POD modes you want to take.
It's more basically a real-time situation.
Yeah.
And on basic desktop computers or something like that, or different
minimum, yeah, minimum 16 GB RAM is required. Otherwise, what happens? Yeah. So what it happened is that you have all the concentration matrices, right? Say M1 by N1, M1 by N1, say N data, N snapshots. Now you make it into columns, right? It will be huge data matrix will be comes out. All the matrices will be clubbed into a single array. So sometimes what happened, if you want to do, suppose you are doing DMD, then followed by the multi-resolution, it will say out of memory. Because there is no memory to store because it is already stored the previous data. So that is up to the user to how to do that. But a simple desktop will be do for my problem.
With 16 GB RAM is good enough.
Good
to start with something, the basics. Okay.
Yeah.
Okay. Thank you.
Thank you.
My voice is audible, ma'am. Can I ask few questions?
Sure.
Yeah, sure.
Yes. So the first one is that whether DT matters, the gap between the snapshot matters, or how you have taken care of that?
It is really for me. What I did is that it is hit and trial method for me right now. That is how you have to train your data.
Okay. So up to how much time you have run the simulations? Up to how much time? Like if you have shown for time up to time t equals to 50, then you have run the code for like time t equals to 50.
Code been run for the whatever time window is there. Okay. But how much data projection you want to do, the POD modes, that depends on you. Suppose you have to, whether you have to do the experiment or you have to do the numerics, there is a time window you have to do the integrations, right?
Yes.
Or run the experiment. That is up to you. Once you did the experiment, you have the data. from the data, you want to study the structures. Now, when you do the SBD, how many you get the rank of U? You get R. Out of R, how many POD modes you require to train your data? That is up to you. It doesn't depend on how much. Yeah, sorry.
Yes. But sir, if we run the code for entire time, then it will add to the cost, like it will consume memory. And also, I just wanted to know if we can reduce time up to that time we can run things like that.
No, actually what happened, I'm telling you, where the DMD comes into picture, you have already the data. Okay, yes. You have already the data either by simulation or by your thing. So what you can do is that, as you are saying, say numerical simulation. So up to what time you can do? Say you suppose the numerical simulation is supposed to, you think that it has to go from 0 to 100 seconds or 100 units of t. Suppose you do for the 50 and train your data. Now predict it, whether you are getting the next level coherent structure correctly or not. If it is, keep on doing with your A tilde or A whatever you're getting from the DMD till up to what time the A operator or this matrix you are getting from the DMD, if gives you the future prediction. The moment you feel or you check with the cross check with your numerical or the experiment thing, if it is not correct, up to that period, the DMD modes predicted future prediction. That much you can do.
Okay. So one last question. So if we get the structures like things like that from the numerical simulations, then where comes the role of DMD? Because we are just verifying that these kind of structures we obtain from numerical simulation. So
right.
Where comes because we have to run the simulations for entire time.
No, what I'm saying, suppose you have to do the experiment, you are doing some experiments, say, validated experiment, say 0 to 100 units. Okay.
Yes.
So take the data for the 0 to 50 units, train them. Now for the 150 to 51, you know the xk plus 1 equal to axk. You know x at 50, x at 101, you can get it. Say that dt is 1. You can get it. You can compare with the original one.
Okay. But if we have to plot the original one, then where comes the role?
Role is that less number of data you can store it. Model will be reduced. Instead of the full nonlinear simulation, you have to suppose you run the simulations from the 0 to 100, but only the dynamics, whatever you are getting, or the relevant coherent structure is only required for a certain amount or certain space or time. So it is irrelevant to store the so much of things and to do the so much of analysis.
Yes, sir. Yes. Thank you, sir.
Sir, I have one question.
So we have another question. Can you please unmute and ask?
Yeah, I have unmuted myself. Can you hear me?
Yes, I can hear you.
Yeah, so my question was, when do we use POD and when do we use DMD? Like, how do we know when to use which?
DMD and which one is?
POD.
POD.
Yeah.
Frankly speaking, I don't know the answer to that one. I don't know to that one, but DMD and POD will be this model things. What the theory says, if your matrix is defect free, all that means the normal one or near to normal, you'll be getting everything correct. Whether you use the model, POD, SBD, or the DMD, everything will be fall into the same category.
Thank you, sir.
Is there any other question? If there is no question, then we can stop this session here with a thanks to our speaker, Dr. Hota. Thank you very much for accepting our invitation and for such a wonderful and interactive session. I must say, a lot of people has interacted. It's a huge success for us. Thank you very much.
Thank you. Thank you, Vikas. Thank you, Sangarshi. Thank you, Satyajit, for the invitation.